Hi, I'm Rebecca Ringett from the Community Coordinated Modeling Center, and here I'll be demonstrating a simple way to use the Komodo Satellite Constellation Mission Planning Tool, which we call the Reconstruction Tool. All right, so first things first, you have to pick what model data you want to use in the reconstruction. So the basic piece of how this works is the reconstruction takes a trajectory of your choice and flies that trajectory through the model data. So this is based on the fly-through that's described in a different video. But the thing with the reconstruction is that you can build a satellite constellation of any number of satellites and a wide variety of arrangements and fly that constellation through, reconstruct what it sees in a variety of dimension choices, any combination of the 4 possible dimensions, which include time. And then compare that to what the model data predicts in a similar reconstruction. Okay, so let's get started. So first you need to decide and enter in what model output you're going to be using, where that output is located. You need to find out what the time range is that's contained in that model output, which can be done through here. Then you need to retrieve a satellite trajectory. So you can pull this in from a file of your own creation. You can pull this in from a previous fly-through result. And all of those things are demonstrated in a separate notebook called Input-Output. I'm not going to go over here. But in this case, I've chosen to use a real satellite trajectory from the Grace 1 satellite. And I'm using the satellite trajectory function from the fly-through to pull that into Python memory. Well, that particular function accesses SSC web, and not every coordinate system imaginable, of course, is possible for the output of the trajectory requested. So you can pick from the coordinate systems they offer, fine, and then you can use the convert coord function that we offer through the utils script in the fly-through to convert to any other coordinate system you want, as long as that coordinate system is included in the SpacePy or AstroPy packages. More coordinate systems will be added in the future. Okay, so once that conversion is complete, you have to choose what variable you want to reconstruct. And you can use that. You can decide that using the variable search function, which was covered in the introductory video. So the next set of options to choose are indicative of how you want the reconstruction to be done. So you need to choose which pair of dimensions you want the reconstruction done in, and it's a pair. You need to choose the analysis method and your grid resolution. And depending upon the analysis method, there can be other things that need to be set as well. So this is the documentation. You can read this thoroughly at your leisure in the notebook on our GitHub. But what I want to cover here is that the recon option is your analysis method option, and that's described at length in the documentation and in the reconstruction talk from COSPAR 2022. So I recommend you dive into that video. So here we've chosen neutral density, and we've chosen a latitude-longitude reconstruction, and we've chosen this particular reconstruction option. So this option takes the given trajectory and does not modify it at all. It flies that constellation trajectory through the data and then grids that data into a latitude-longitude grid whose resolution is chosen here by the user. Then that longitude-latitude grid is flown through the GETM data, the same GETM data, at a range of times and heights. That's what this average D slice means. And at what times and at what heights, or what resolution on that grid, rather, is chosen right here by the user. So this is seconds, since that's the time dimension, and this is Earth radii. How do I know that's Earth radii? So you can come back here. This coordinate conversion converts the geographical Cartesian coordinate system into a geographical spherical coordinate system, which has the typical longitude range, -180 to 180, typical latitude range, and its vertical component is in Earth radii, as hinted at here. You could print the units if you want confirmation on that. Okay, so that's Earth radii. Now, if you choose a finer latitude-longitude resolution, you're likely to have more holes in your reconstructed plot or the predicted observation of your constellation satellite. And that's simply due to satellite coverage. For your D1 and D2, the resolution of the various slices with that longitude latitude grid flies through the data. The time and the height resolution are up to you, of course, but the finer you make it, the longer it takes to run. So choose wisely. Okay, so once all of that is decided, you can execute the reconstruction call. One thing to keep in mind is your constellation arrangement. So here I have a reasonably simple constellation arrangement, and it's 6 satellites, indicated by how many values I have in this list, and they're offset by 30 degrees in longitude each. You can have offsets in time, you can have offsets in latitude, height, whatever, what have you. And it can be in spherical or Cartesian coordinate systems. The other reconstruction notebooks show how to do it in those cases. Right. Whatever offsets you have, make sure that makes it into the execution, and it goes. As existing in this notebook, the complete process took about 6 minutes to run. And it outputs 3 things, 3 functionalized data sets. First, this density, this neutral density variable, is the reconstructed observation of what we expect the satellite would see based on the model data and based on the given trajectory and constellation arrangement and configuration. Row N model is what the model predicts for the same trajectory, same reconstruction method. And %diff is basically just the % difference between the two. So you can perform analysis on this as demonstrated in other notebooks. All I'm going to show here is just a nice version of the default plots so you can see what this means. All right, so this is what the given constellation configuration is expected to see right there. This is what the model data predicts. And the % difference is given by the %diff variable. And as usual, this is a fully interactive plotly plot. You can pan in, you can go back home, you can save a picture, and you can even save their interactivity through additional code. Okay. And there's a piece of code down here showing your concocted way of getting a histogram with a % difference. Of course, a % difference of 0 means it exactly agrees, and anything off of that is, of course, not perfect agreement. All right, so this has been a basic introduction to the reconstruction tool, also known as the Satellite Constellation Mission Planning Tool. We've developed this to support the GDC mission, Geospace Dynamics Constellation mission, and there are additional features that fulfill the requirements that the science team asked of us. So feel free to dig into the notebooks, grab your data, grab your Komodo, and have fun. See you in the next video.